Well, I should say I'm very grateful to the organizers, in particular to Jens, for having encouraged me to say a few words here. It doesn't really fit into the program because, you know, although I guess I was, there were times when I had a sort of passing interest in matrix models, but I don't remember what they are. But I still keep a very lively interest in matrix mechanics. So this is about matrix mechanics. And it will sketch a view of quantum theory that will result in the insight that quantum theory is not about one algebra. It's about the filtration of algebras, many algebras. So that's very important to anticipate something. So let's see how it goes. This is a somewhat slimmed down version, Jens, of what I showed you, just to, so that you won't be worried. I think I should get through in an hour. So here is a table of contents. I will briefly tell you what I'm going to tell you. Then I want to recall a very, very simple standard argument why physical theories are never predictive. There is not a single physical theory that can be used to predict the future. Then I want to briefly recall why relativistic quantum theory should satisfy locality in the sense of Einstein causality. Then I will present to you the ETH approach to quantum theory. Then I briefly have to talk about what an event is in quantum theory and how to detect one. And then I would like to sketch the relativistic version of the ETH approach. This is a somewhat recent development. I'm not pretending it has already reached its endpoint. And then we will summarize. Here are credits. I had many discussions with many people, and several years ago I had a last PhD student who was a very pleasant partner for discussions and efforts in this direction. Baptiste Chubnel, he's actually French, but he had the misfortune to get married to a Swiss wife who refused to gypsy around, and so he gave up his academic career, in spite of the fact that I think he might have been very talented for one. So what this lecture will be about. I will outline some new foundations for quantum mechanics. It is called the ETH approach to quantum mechanics. E stands for events, T for trees, and H for histories. The approach enables us to introduce a precise notion of events into quantum mechanics. That's something that Rudolf Haag always emphasized. He said we have to know what events are, otherwise we won't understand what quantum mechanics is about. And so I've tried to sort of follow up on his proposal. Then I explain what it means to observe an event by recording the value of an appropriate physical quantity. And I will then exhibit the stochastic dynamics of states of isolated open systems. States do not evolve according to the Schrödinger equation, as is mistakenly claimed in almost every course on quantum mechanics. Then I want to focus on how quantum theory could be reconciled with relativity and what it tells us about the fabric of space-time. And that's about it. So the specific topics that I should address, and of course I will not be able to talk in depth about all of them, are as follows. Foundations of quantum theory. So why are physical theories never fully predictive? That will come just next. Why is quantum theory intrinsically probabilistic? What are events? How do we measure physical quantities and detect events? What is the role of time in quantum theory? Unfortunately, I had a flu, and so I missed almost all the talks at this meeting, very regrettably. But those that I heard didn't feature time.
But there were. We did feature time.
Oh, you did? Yeah. Very good. Yes. So, good. Locality and Einstein causality, I already mentioned that. So, what are the basic problems that in coming up with a framework that unifies quantum theory with the theory of space and time? Of course, I wish I knew the answer. I'm not quite sure what to say about it, but we will say a few superficial things about it. I tend to believe, and I will argue why, that a consistent quantum theory of events must necessarily be relativistic. I think non-relativistic quantum mechanics ultimately doesn't really make sense. Okay, and then of course we want to speculate a little bit about whether space and the causal structure of space-time might in some sense emerge from quantum theory. So, what prevents theories from being fully predictive? This picture is less nicely visible than I was hoping. You see, the black line is my world line. And I'm at the moment at the space-time point that is labeled present. I have access to some of what is inside my past light cone. I may have received signals from events that happened inside my past light cone, but I have absolutely no access to events that happen outside my past light cone. And they might be, these events might be so drastic that they might kill me, maybe in 5 minutes, but they might also kill you. And so whether you think classically or quantum mechanically, it is obvious that because of a lack of knowledge of initial conditions, we can never predict the future with certainty. So the past is a history, the past for a creature like myself is a history of events. These are these blue little things that you see here. And the future is an ensemble of potentialities of which I cannot exactly predict what they will be. Now, I believe this fundamental difference between past and future is an essential element that should be retained in a sort of reasonable formulation of quantum theory. You have a question or comment?
The definition of past and future, or
so the problem is I had this flu and I don't hear very well.
Yes, okay.
So
speak up.
yes.
So if you take any conventional physical models, we have equations which are reversible in time.
Yes.
We can run them forward and backward.
Yes.
So what distinguishes on this diagram future from the past if we just make involution and relabel all future?
So you see, the past is something I have experienced. It's in my book of photographs and my diaries and so on.
Well, book of photographs and etc. It's a space-time event which is located in that point.
Yes.
Denoted by present is what you have now.
Yes.
And it's just the current state of moment. It's not that. It's not necessarily. You see what I'm trying to say? You don't. In that photograph, you have a print of the past,
yes.
which you call past. But in reality, what you do, you trace the equations, the physical models, and your experiences to the past, and you make a conclusion that what is drawn on a photograph happened some times ago. But it's just in the present moment. It's located in that point, in that black.
Yeah, I'm listening, I'm following.
You can try to run physical equations not to the past but to the future, make prediction for the future.
Yes, you see, the problem is you have the wrong idea what the physical equations are, but you're in good company. With my exception, I think almost everybody in this room has the wrong idea about what physical equations are. But you have to wait a little bit till you understand why I'm saying that. And of course, I will, Jens, I will add 3 minutes at the end because I already answered a long question.
Could you please add 4 minutes, because I would like to make a small comment.
Yes.
I'm very, very happy that you put the black dot in the middle of the line.
Yes. But it doesn't mean that I will grow up to an age of 150. Okay. All right. So that explains why even classical theories are not really predictive. Now let's go to quantum theory. Can this be somehow my sketches are not so visible? That's a shame. So this is a Gedankenexperiment which I worked out with Schubnel and with Jérémy Faupin from MITS actually. So let's look at the system that is the composition of 2 subsystems. A subsystem confined to Q and another subsystem which in fact just consists of a particle P whose orbital wave function is prepared in such a way that it will propagate into a cone opening to the right. The cone is unfortunately not visible anymore. And the point is now that very reasonable time evolutions, quantum mechanical time evolutions, have the property that the evolution of P is essentially independent of the evolution of the degrees of freedom of Q, even if Q has very many degrees of freedom, simply by cluster properties of the time evolution. Now we look at the concrete realization of this setup. Q consists of a spin filter that measures the component of the spin of a particle in the z direction. And it consists of a particle P prime whose orbital wave function is prepared in such a way that it propagates into a cone opening to the left and hitting the spin filter. All right. And now I prepare particle P and particle P prime in an initial state that is a spin singlet. And then I let time evolution set in. Let's make the following assumptions. Let's assume that the Schrödinger equation describes what will be seen in the experiment. Just the Schrödinger equation. Thibaut has probably left. He's an advocate of the many worlds interpretation, and these people claim that the Schrödinger equation describes everything. Now, I want to show that this cannot possibly be correct. So let's make the following assumptions. P and P prime are spin 1/2 particles prepared in a spin singlet initial state. The spin filter that will measure the spin of P prime in the z direction is in a very poorly known initial state, which is not entangled, or at least not necessarily entangled, with the initial state of P prime and P. The dynamics of the state of the total system, everything together, is assumed to be fully determined by a Schrödinger equation. In particular, it follows then that the initial state of the spin filter must determine whether P prime will have its spin upwards or downwards. If it has the spin upwards, it will pass through the spin filter. If it has the spin downwards, it will be absorbed by the filter. I also want to assume that the correlations between the outcomes of a spin measurement of P prime and of a subsequent measurement of the spin of P are as predicted by the standard quantum mechanical assumptions that have been tested in the experiments by Aspe and Chizin and so on. So let's assume that these correlations are the way the experimentalists tell us they are. Now, there is the following fact that I already mentioned. The Heisenberg picture dynamics of observables, such as the spin referring to the particle P, that, remember, propagates into this cone opening to the right. This Heisenberg picture dynamics is essentially independent of the dynamics of the degrees of freedom of Q. So this follows from our choice of the initial conditions of the orbital wave functions of P and P prime and of cluster properties of the time evolution. Here one has to do some analysis. It's not a totally trivial statement. Well, it then follows that the spin of particle P is essentially conserved up to very slow, small corrections before it will eventually be measured, say, in a Stern-Gerlach experiment. But P and P prime were initially in a spin singlet state, so the expectation value of the spin of P will be the way it was at time 0, namely close to 0 for all later times. However, this contradicts the third assumption, because if P prime, for example, is seen to have spin up, then P should have spin down in order to satisfy the usual correlations. But apparently the Schrödinger equation doesn't predict that. So it follows that the Schrödinger equation can never predict the outcome of experiments in quantum mechanics. This, of course, may sound trivial, but people seem to tend to forget it. So it also suggests that the predictions of quantum mechanics are all probabilistic. Now we have to briefly address the problem of locality of quantum theories. So let us assume that the Copenhagen heuristics is correct in the sense that if the spin of particle P prime has been measured to be sigma prime, which is up or down along the z-axis, and the spin of P has been measured to be sigma, which is also up or down, but along an axis n, then the state of the system right after these two measurements is a simultaneous eigenstate of the two projections P pi of P prime sigma prime Ez. It's the projection that measures on spin sigma prime in the z direction for particle P prime, and the projection pi p sigma n, which projects onto a state of particle P with spin sigma in the direction of the axis n. And the state is a simultaneous eigenstate of these two projections corresponding to the eigenvalue +1. That's the usual Copenhagen heuristics.
Wait. When you were saying that the 2 points of view are not equivalent, you are saying the Heisenberg picture is okay for isolated systems. You are saying the Heisenberg picture is okay for...
The Heisenberg picture, in contrast to the Schrödinger picture, is a totally safe building block for quantum theory. You see, you might even agree, although Schrödinger was probably a much better mathematician than Heisenberg, but Heisenberg had a much deeper understanding of what quantum mechanics was. All right, so now, so it is possible that these two spin measurements are made in space-like separated regions of space-time, so that the localization regions of these two projections are space-like separated. The order in which the two measurements then occur depend, of course, on the rest frame of the observer, who records the data of both measurements. But in order for the prediction of the correlations to be unambiguous, it cannot matter whether you first apply pi p and then pi p prime, or in the other way.
This is why they commute.
And that suggests that they should commute. Of course, this implication is logically a little bit too strong. They might just commute on all states on which such measurements can be made. But let's be a little generous and say they have to commute. This is really the right way of understanding local commutativity in relativistic quantum theory, I think. All right, so that's that much about locality. Now I would like to sketch the ETH approach. So, in fact, the basic problem I want to tackle is to clarify the notion of an event featured by an isolated system. I will always look at isolated systems. Why is that? We have a very clear idea about Heisenberg pictured time evolution for isolated systems. If we look at a system that potentially interacts with an environment, we don't know how to describe time evolution in a conceptual way. To say that the system is isolated doesn't mean that it is closed. It can still release signals to the outside world. So I look at open, isolated systems. All right. So, as I already mentioned at the beginning, I think time is certainly an absolutely fundamental quantity, and so I want to involve it into my discussion as much as possible. Let's suppose the present time is t0, and let I be an arbitrary interval of future times. Here is a definition. I consider an isolated open system S, then potential future events in S are described by certain orthogonal projections labeled by time intervals in this interval t0 infinity after the present. The star algebra generated by all potential future events by such families of orthogonal projections is located in a future interval I of times is denoted by E sub I.
I mean, this is your understanding of time, but I mean, you are not saying that all events are just labeled by the time. This is a filtration by time.
Yes, I mean, you will see that this picture will then be refined. So that's E sub I, the algebra generated by potential events occurring at times inside this interval I. If I take the algebra generated by all E sub i's where I is contained in the interval t infinity, I get an algebra that I denote by E greater or equal to t. And E is the one generated by all of them. Temporarily, these closures are closures in the operator norm. But here in the definition of the E greater or equal to t algebras, it will become crucial to pass to Wick closures once representations are chosen. All right. Now, just by definition, it is obvious that EI contains or is equal to EI prime whenever I contains or is equal to E prime. E greater or equal to T contains or is equal to E greater or equal to T prime if T prime is larger than T. Now, quantum mechanics of an isolated system is defined by a filtration E greater or equal to T of algebras of possible potential future events. That's sort of a good picture about how to introduce a quantum mechanical system. It's of course not usually what we do in our courses. You see, most people believe, and it's in fact a fact, that these algebras E greater or equal to T are independent of T. If you look at the system with finitely many degrees of freedom, then the potential events are projections that can be viewed as functions of the momentum and the position operator, and then E greater or equal to T is independent of T.
Up to isomorphism.
Yes, but but the algebra, really, if you look at these algebras,
They don't change.
they don't change. They're all the same, right? And that's, of course, a problem. Most of what we do in our courses on quantum mechanics is to talk about quantum mechanical systems that do not feature any events. It's like, talking about black holes during the entire course. That's a little disappointing. So here is a principle that will guarantee that events will be possible. And I call it the principle of diminishing potentialities. It says that E greater or equal, for a realistic model of quantum theory, E greater or equal to T contains but is not equal to E greater or equal to T prime. The greater or equal is missing here. Whenever T prime is larger than T. Okay? So this you should try to record. I think this is important. Unfortunately, people have troubles believing that this is a reasonable principle, because in our discussion of simple examples of quantum mechanical systems, it's never true. It's unfortunately the E greater or equal to T's are all the same algebra. Okay, now as I said, it's important to actually imagine that these are von Neumann algebras. So we should introduce states and representations and so on. The state on these algebras is defined in the usual way. And now let's call it omega, say. Then I set omega sub t to be the state omega restricted to the algebra E greater or equal to T. Okay. Now it is perfectly possible that omega is a pure state on the C-star algebra E. But since E greater or equal to T sits inside E properly, it might be a mixed state on E greater or equal to T, just by entanglement. In fact, for realistic models, the algebras E greater or equal to T will be type 3-1, I believe, and then there are no pure states that are continuous. Okay, so we should not, in fact, it is another mistake we do in our courses on quantum mechanics. We always do as if pure states were sort of what we should talk about. But in fact, pure states never appear in nature. Only mixed states appear. And here you now understand why. All right. So this observation that states restricted to E greater or equal to T tend to be mixed opens the door towards a clear notion of what might be meant by events and to a theory of direct measurements and observations of events. So I defined the notion of potential future events, and I now want to render it a little more precise. So we say that the potential future event that might happen inside us at some times greater or equal to T is given by a family pi sub psi of disjoint orthogonal projections contained in an algebra E greater or equal to T that add up to the identity. Okay, that's a potential future event. Now, in accordance with the Copenhagen mumbo-jumbo, it appears natural to say that the potential future event actually happens in the interval T infinity of times if the state omega restricted to the algebra E greater or equal to T looks like an incoherent mixture of states labeled by these projections pi sub psi. Right? Because if an event happens, you say that the off-diagonal interference terms should disappear, and so...
If there exists omega such that...
Yeah, the reduced. I should maybe have written here a T, but in fact all these operators are in E greater or equal to T. I'm sorry for a few misprints. So omega T, namely omega restricted to E greater or equal to T, should look like an incoherent mixture of states that are in the range of these projections pi sub psi. Okay? Is this clear? At least for people who know a little quantum mechanics, I guess it's pretty clear that this is a reasonable mathematical expression of the Copenhagen stuff. So, for an operator x in E greater equal to t, we define the adjoint action of x on the state omega t to be the linear functional given by minus omega t, by the expectation of the commutator of x with a in the state minus omega t.
Yeah. Okay, so you mean this was saying that they are sort of diagonal in the same basis, and this is a commutation that you write at them.
Yes, so now of course 5 implies and is implied by saying that add x omega t vanishes for all operators x generated by these projections. Okay. All right. Now in the following we consider some stratum of physically important states. This is in fact, I think, the weak point of all these discussions. We have major problems in general quantum theory, also in quantum field theory, to specify what we mean by physically important states. And I will leave this a little bit vague. I cannot, first because I don't know much about it, and second because in 1 hour one cannot clarify everything anyway. All right, and then with respect to the stratum of physically important states, we always will look at weak closures at von Neumann algebras. But I don't change my notation. So here is a slightly abstract version of what I just went through here. If M is a von Neumann algebra and omega is a state on M and X is an operator in M, we say that add X omega is a linear functional which when evaluated on A is given by the expectation of minus the commutator of X with A in the state omega. The centralizer of a state on the algebra M consists of all operators X in M whose adjoint action on the state omega vanishes. This is a subalgebra which is very easy to see. It's in fact a star subalgebra. And omega is a normalized trace on this centralizer. And so we know the possible structures of these centralizers completely. The center Z sub omega of the centralizer is defined to be all operators in the centralizer C sub omega which commute with all other operators in the centralizer, as usual. So now we are prepared to introduce the notion of what an actual event is. So again, let S be an isolated open physical system. Here is a definition. Given that the state omega t is the state of S on the algebra E greater or equal to t, an event is happening at time t or after or later if the center Z sub omega t contains at least two non-zero orthogonal projections, pi 1 and pi 2, that are disjoint and that have a strictly positive expectation value with respect to omega t.
But when you say an event, what do you mean?
Pardon?
When you say an event is happening, you mean something is happening. What do you say?
An event is happening if this condition is true, and I will tell you what it means for the event to happen. So, but that's so far a definition of what I mean by an event is happening, and I will then interpret it. So, since I'm a simple-minded person, I would like to assume that this center Z sub omega t of E greater or equal to t is generated by a discrete family of orthogonal projections. It could also be a continuous family, but it's a little easier to argue with discrete families of orthogonal projections where labeled by points psi in x sub omega t. X sub omega t is simply the spectrum of the center of the centralizer. I assume this spectrum of the center of the centralizer is a countable set. Here is an axiom that will clarify what I mean by saying that an event is happening. Suppose that the cardinality of the spectrum of the center of the centralizer is at least 2, and there are 2 projections pi sub psi, psi in x sub omega t, for at least 2 different points psi that have non-zero expectation in the state omega t. Then to say that an event happens means that the state omega t must be replaced by one of the states omega sub t and psi that are given by sandwiching everything between pi psi. For some psi in the spectrum of the center of the centralizer, so with the property that omega t of pi psi is non-zero. The probability for choosing a certain psi, meaning that I choose the state omega t psi to make predictions about the future, the probability of picking a psi is given by Born's rule.
So you mean this is a reduction of the wave?
This is the reduction of the wave function. But here it is, you see here it sort of comes naturally. You don't have to say that because Henri has made a measurement, the wave function collapses. It is coded into this filtration of algebras.
But then it generates a tree, of course.
Pardon?
It generates the T of the ETH.
Absolutely. Yeah. I wish I didn't realize that these pictures come out so poorly. It's terrible. So, apparently the time evolution, you know, if you believe that this is a good point of view, you conclude that the time evolution of states of an isolated physical system S is described by a stochastic branching process, with branching rules as determined by this axiom and Born's rule. And the possible futures given the present here is denoted by this cross, and the system is in a state rho. The future is a tree-like structure. And the future that we will actually experience will be one path on this tree, and that's called a history. Now, this shows, of course, that the evolution of states in quantum theory, as soon as you talk about the quantum theory with events, the evolution of states is not given by any Schrödinger equation. It's given by a stochastic process like that, although the Heisenberg picture evolution of observables is the way it always was. Now, I would like to emphasize, some people believe that this is just a, you know, somewhat abstract version of the decoherence mumbo jumbo, but it's actually totally different. I could go into that. The decoherence mumbo jumbo attempts to impose some kind of Markovian structure on the sequence of observations or measurements. This is very non-Markovian. Okay. Although we would have to clarify what we mean by Markovian in quantum theory. Anyway, it's really very different. Now, pardon?
It looks close to a path integral.
No, it has nothing to do with a path integral, because I'm not talking about amplitudes.
No, I understand, but it's still...
Maybe it might remind you. And then, you know, I cannot prevent you from being reminded.
But in a path integral, you don't have to talk about just amplitude.
Pardon? You have?
Path integral, you don't have to talk about just amplitudes. You have the wave function, square modulus is given by 2 paths.
Yes.
Which should track close together for a physical system.
We have to discuss that at the end. All right, so how would you record an event or detect that an event has happened? Let's see. Well, you see, that depends now on who I am, whether I have good eyes or good ears or not so good ears, or whether my brain still works or not so much. Depending on people who record events, they have a certain list of physical quantities available that they are able to measure or observe. the physical quantities available to a certain observer is denoted by O sub S. This is neither a linear space nor an algebra, so it's just a list of abstract self-adjoint operators representing physical quantities that, let's say, Gurab can measure. All right. So then, of course, for any abstract physical quantity y hat and a given time t, we should specify a concrete self-adjoint operator y of t inside this algebra y greater or equal to t that represents the physical quantity at time t. For an autonomous system, the operators yt and yt prime are conjugated to one another by the propagator of S first understood by Heisenberg. So, suppose that at some time t an event happens, meaning that there is some kind of maximal family of disjoint orthogonal projections, pi sub xi, contained in the center of the centralizer of the state omega t, given this algebra y greater or equal to t. And this family contains at least two elements with positive probability of occurrence. Let's look at the operator yt that represents y hat at time t. Here is its spectral decomposition. The etas are eigenvalues of y, and the pi sub eta of t are the spectral projections of these operators y of t. We then say that y of t can record the event happening at time t if basically the spectral projections of y of t are inside the algebra generated by these projections little pi of xi. Now, unfortunately, there is very little chance that they are exactly in the algebra, but they should have a small distance. And what the distance is can be clarified using conditional expectations. Pardon?
You mean the distance in norm or in conditional expectation?
You see, there is always a conditional expectation of every operator in E greater or equal to T on Z.
Okay, using the state.
Yes. And then, yes. So
you need both the filtration E over T and omega.
Pardon?
Everything depends on the choice of a state plus the filtration.
Yes, yes.
Yeah.
Absolutely. Yes. Well, a state, is not always the same state. The state sort of branches whenever there is an event. Okay. So, well, in that case, we say that the quantity y hat can be used to sort of detect an event of this sort. This is a little bit brief, but in fact this can be made totally precise. I just don't want to go into further details for reasons of time. Now let's pass to the relativistic setting. So this is again my word line of JF. I do not indicate here my death, Jens. I'm at the moment at this space-time point P sub t. But I used to be a little while ago at the space-time T0 that was in main station in Zurich. The E greater or equal to T should now probably be identified with all operators, functionals of, say, fields, electromagnetic field and so on, that are localized inside the forward light cone erected over the space-time point PT. The E greater or equal to T naught that was available to me when I was still back in Zurich are all fields localized inside the forward light cone V plus PT naught. That obviously contains the red algebra. It is also now clear why this principle of diminishing potentialities might be true and how this might depend on dimension. You see, suppose my theory has massless modes, such as the photon and the graviton and so on, then it could have happened that some, for example, that I don't know whom, but probably Jens wanted to call me at some point in the future of PT naught, but in the past of PT. And unfortunately, my cell phone was turned off.
You never had one.
I have one, and I can be called, but I don't use it very often. So if it was turned off, then his message zoomed out along the surface of a light cone in between the red cone and the blue cone, because electromagnetic waves travel at the speed of light. I will never be able to detect his message because I cannot catch up with photons. They are always faster than whatever I can do. They will never penetrate the photons that Jens created here in this little double diamond. These photons will never come into the inside of the red forward light cone. So they are lost forever. This means that the relative commutant of E greater or equal to T inside E greater or equal to T naught is a big algebra. It consists of all asymptotic electromagnetic fields located in this region here. So it's an infinite dimensional algebra. In fact, this was something that Buchholz first analyzed in fairly great detail in connection with a scattering theory for photons. So I think, I'm not quite sure when he formulated the theorem, but it goes as follows. In a relativistic quantum field theory in even space-time dimension with massless particles, the algebra E greater or equal to PT of all physical quantities observables potentially measurable in the future of the space-time point PT is of type 3.1, and the relative commutant is type 3.1.2 actually. Now this is a result of what might be called Huygens principle. This will not be true for relativistic theories in odd-dimensional spacetimes. So you see, probably the fact that our space-time is even dimensional has a fairly fundamental significance. It is one of the ingredients that enables us to understand what events are. Okay, now you see, I did as if relativistic quantum theory depends on my presence. I would now like to take myself out of the picture and make it independent of individual agents. And so that goes as follows. This is now a little bit stupid, but I don't know how to do it better for the time being. Probably at some point this will be superseded by more reasonable formulations. Let's suppose that M is some manifold, say topological space is enough for the moment. I consider a fiber bundle, quantum mechanical F, whose base space is given by M, and the fiber above a point P in M is given by an infinite dimensional von Neumann algebra that I denote by E greater or equal to P. We assume that all these algebras are isomorphic to a given one, namely, for example, to this type 3.1, hyperfinite type 3.1, say. Okay. Now we say that the point P naught is in the past of a point P, written as P naught precedes P, if there exists an injection map, iota, that maps E greater or equal to P into E greater or equal to P naught. It enables us to identify E greater or equal to P with a subalgebra of E greater or equal to P naught, and with the property that the relative commutant of iota E greater or equal to P intersected with E greater or equal to P naught is actually an infinite dimensional non-commutative algebra. Pardon? Sorry, what?
you misprint in
oh, okay, thank you. You looked critical, Alain.
Yeah, I am critical. Let me tell you why. Because I think that such an injection can be found in all cases. I mean, I don't think it's precise enough. You see, it's not that there exists abstractly an injection, because I think this will always exist. I think you wanted to satisfy some first.
Yeah, I agree with that. I agree with you, yes. In fact, I'm not quite sure how to say this more precisely, but maybe you can.
You should say it more precisely,
Yes.
because as it is, I think it's empty.
Yes. Well, you see, from the picture, we sort of know what we mean. So we have a point P naught here, and then this is the forward Lie cone, and then P is here, and then obviously this algebra is a subalgebra of this
Sure,
one.
but I mean, you want to say it better than what you're used to make.
All right. So this relation will introduce a partial order on M.
No, in fact, I mean, this is part of the structure. I mean, giving these maps is part of the structure. You cannot just say they exist, you see.
Part of the structure. Absolutely, yes. All right. And then it could happen that 2 points P naught and P are neither in their, that neither P naught is in the past of P nor P in the past of P naught, and then we say that they are space-like separated, written like this. So these relations will determine a causal structure on M.
Is to take it in the beginning.
Yeah.
Pardon?
You say determine the causal structure, but what Alain wants is to have it from the beginning.
Yes. Okay. So now we have to reintroduce events in this setting. E greater equal, let sigma be some space-like hypersurface contained in M that contains a point P. E greater equal to sigma is then the algebra generated by all the E greater equal to P primes, where P prime belongs to this surface sigma. Definition. We say that an event happens in the point P if the center Z sub omega sigma E greater equal to P of the centralizer C sub omega sigma is non-trivial and contains at least 2 projections with positive probability of occurrence, just like before.
So you have a choice.
Pardon?
You have a choice between these 2 projections. That's the point.
Yes. Well, you know, in the end it will be probably infinitely many projections, but you need at least 2, otherwise no event happens. So the axiom is, this is now an important axiom, compatibility locality. If 2 points P and P double prime of M are space-like separated, and events pi P sub psi and pi P double prime sub eta actually happen in the points P and P double prime, then they should commute. This, of course, is somewhat related to the locality discussion I gave at the beginning of this talk. Okay? Yes, Jens?
Yes.
Good. So they should commute. This, I believe, will have something to do with introducing geometrical structure on M, but I don't understand this so well yet. So you see here is a graphical representation, an event happening in P and an event happening in P double prime, but the 2 people in P and P double prime cannot see each other's event yet. All that P can actually see are events that have happened in the past Lie cone of P. So now I would like to describe histories of events. I choose a space like surface sigma with the property that some bounded subset of sigma lies in the past of a certain point P, as shown in the following figure. Here is sigma, here is P, and if I intersect the passed light cone in P with sigma, I get this disk-like region. Now in the past of P, all kinds of events may have happened. I would like the prediction of whether an event happens in point P not to depend on anything that is space-like separated from P. That would be terrible. It should only depend on what has happened in the past light cone of P. Okay, and so let's see why this works. So we would like to say that the events, the initial condition chosen on sigma and the events that happened in the past light cone of P actually determine the state omega P that I have to consider to decide whether an event happens in the point P or not. Okay. And so here is why this works. Here is an inductive hypothesis. P1, P2, etc. are all the points in the past of the point P, but not in the past of any point on the initial condition surface sigma. With any of these points, we can associate an orthogonal projection, pi super pi sub xi I, where xi I is in the spectrum of the center z super pi sub omega pi. And this projection actually represents the event that happened in the point pi or its future. We define so-called history operators. History operators are ordered products of these projections. Now we have to make sure that this ordered product is well defined. Well, if pi is in the past of pi plus 1, then in fact pi will stand to the left of pi plus 1. But if they are space-like separated, the order doesn't matter because they commute. So this shows that this ordered product is totally unambiguously defined.
It's a time-oriented product? Or?
Yeah. Right. So then we said, we define the state omega sub p on the algebra e greater or equal to p to be given by...
But you mean it's no longer a projection, of course?
Pardon?
It's no longer...
No, this is not a projection. It's a product of projection. But the omega p is now given by this particular state. You see, this is just iterating the rule we had before, going through all the events that have happened. And the important thing is we only consider events in the past light cone of P. And okay, and here is the generalized Born rule. Now we can do the induction step. So we can now answer the question whether an event happens in the space-time point P or not. Well, an event will happen if the center Z sub omega P of the centralizer of the state omega P given the algebra E greater or equal to P contains at least two disjoint orthogonal projections with strictly positive probabilities in omega P. Then we can go on and, I mean, that's the induction step. I think it's quite clear that the compatibility locality axiom can be expected to yield non-trivial constraints on the geometry of space-time in the vicinity of space-like separated points in which events happen. But this is something I don't really understand very well yet, so I don't want to confront you with half-baked ideas about this matter. It's time to stop. I think I'm pretty much within my given slot. So here,
You have extra 4 minutes.
okay, so here is a summary and a few conclusions. So I think, as in the genesis of special relativity, the electromagnetic field or other fields describing massless modes will actually play a key role in the genesis of a consistent quantum theory that talks about events and solves this, what people call the measurement problem. I do not believe that this has been appreciated. I mean, I'm an old man, and it is unlikely that old people have very original ideas, but I think this is an idea that has been overlooked as far as I can say. In particular, we have understood that apparently, if we believe that my notion of events is reasonable, then presumably space-time will have to be even dimensional, because Huygens principle is wrong in odd-dimensional space-times. I believe that, as in the genesis of general relativity, the causal structure of space-time will play a key role in the functioning of a relativistic quantum theory. The non-commutative nature of quantum theory and the compatibility locality axiom governing the relations between events that determine the causal structure on space-time. In fact, the events in this sense in which I've introduced them are really what weaves the fabric of space-time. You see, eventually I would like to give up any prejudice about space-time and just reconstruct it from this notion of events. Yes, and so, okay, well here. There is obviously a very natural arrow of time. You know, we always wonder why is there irreversibility, but in fact the right question is why should we have expected anything to be reversible? I think nature is simply not reversible, and you cannot formulate a reasonable quantum theory that describes measurements and facts and events that is reversible. And in this approach, the reversibility has automatically been eliminated by this kind of stochastic process that describes the evolution of states. So this is all I wanted to tell you, and I thank you for your attention.
Okay, any questions and comments?
Martin.
Of course, I like very much that you put the observables in front and states. I like very much the idea to put the observables in front and the states which make the...
But I did not do that.
You said Heisenberg is better than Schrödinger.
No, but yes, that, but not that the word observables is ill-chosen. You see, it's really the potential events that play, that's a better notion than the notion of observables. Because an observable only, the notion of an observable only makes sense when there is an observer. But you know, most of the time there are no observers. But anyway, yes, good.
I just have a question. The word propagator
Yes.
was on it. So you said when events and their detection, so you said an autonomous observer. So do you specify when you just give the axioms for these, say, filtered algebra? Will there also be an among this, say, unitary, what would you say, continuous unitary curve of which resembles a propagator? So there was the word propagator.
Yes. So you see, in an autonomous system, it sort of makes sense to say that an operator, say a functional of fields, that is labeled by a, let's label it by a space-time point. And the same observable in another space-time point, they should be related to each other by conjugation, and the operator that conjugates them is the propagator.
Yeah, this is clear, but do you give this in advance? I mean, if you make a list of axioms. So
You don't have to.
the ETH.
You don't have to.
You see, well, I mean, I wish I could do computations like all the other people did in the other talks I heard. This is very abstract. I cannot do computations. But ultimately, the basic object is this filtration. Okay? If in the non-relativistic regime, there is no problem because time labels everything. In the relativistic regime, it's these E greater or equal to P's. Then it becomes a little more delicate. Now, you see, as many of us, we are somewhat indebted to Buchholz and his clear views of algebraic quantum field theory. He wrote a paper with the late John Roberts about QED, and there, they looked at these. In fact, I didn't know about that initially, but Buchholz explained it to me. They looked at these algebras of fields located in forward light cones, and they said time evolution can be reconstructed from the way these algebras are embedded into one another. They have a discussion of that. So that has already been sort of studied, that problem. But maybe you have, maybe it was a little vague, or is it okay? Maybe we can render it more precise afterwards. Yes.
I have two questions. The first one, I think we agree what's the meaning of probability in the framework of the Copenhagen interpretation of quantum mechanics. But at some point of your talk, you wrote something probability in index T. What does it mean operationally?
Well, I wish I understood what you're referring to, but I can try to guess. It was not probability T, but probability omega T. The probability of seeing the event psi happening.
Maybe I missed it.
What?
I didn't remember the omega, maybe I missed it.
But I think that's what was written. So that's simply omega, omega T of pi psi. Now, you see, you could, I could be kind with you and interpret your question in a sort of deep way, namely, what does it mean for theories where things cannot be repeated arbitrarily often to be probabilistic? And that's a somewhat tricky question. I have thought about it. If you now ask me to summarize my view in 2 minutes, I'm going to fail. I'd be happy to discuss that with you. But I think it does make sense. You see, it makes sense in a similar way as it makes sense to apply notions of probability theory to interpreting the CMB, for example, the fluctuations of the CMB. Right? So if you believe you understand that, you should also understand this. But you had 2 questions.
Yes, the second one, what the Huygens principle play a fundamental role on.
Pardon?
Huygens principle
Yes.
play a fundamental role.
Absolutely.
But we know that even in classical background, on a generic classical background, curve background, the Huygens principle is not valid because there are tails inside the light cone. So would that mean that on a classical geometry, but not flat, all your construction will fail?
No, you see, I only need Huygens principle in the Huygens principle is the same as the principle of diminishing potentialities. What I need, and I wish I could replace it by a weaker formulation, is that if P is in the future of P naught, say, then I would like the commutant of E greater or equal to P intersected with E greater or equal to P naught to be non-trivial. That's the way in which I need Huygens principle. And, you know, I'm sort of fairly confident.
It's bigger than what you see.
Okay.
Okay.
Maybe one last question. So,
Yes, I'm not sure I understood the meaning of event in quantum.
You have not understood it.
I'm not sure I understood it.
Well, I'm also not sure. One can never be sure. But can you be... But is that your question?
Yes, this is my question. What is an event in quantum physics?
Well, then I have to repeat my talk, which doesn't make too much sense, probably. I can just give you the definition once more, if you like. Oops.
Can you give a description in words of what is an event? Without formulas.
Yes. So we saw that in a reasonable quantum theory, these algebras E greater or equal to T, let's talk about non-relativistic for the moment, it's a little easier, get smaller and smaller. In other words, what I can still learn about, possibly learn about, you know, life and the universe and so on now is really less than what I could learn 10 years ago. That's the basic principle. If you accept this principle and you prepare a system in a state that may be perfectly pure as a state on the entire big C-star algebra of everything, then when you restrict the state to one of these algebras, E greater or equal to T, it will look mixed. Is that clear? That's what entanglement is about. You have to talk louder because I don't hear so well. But I assume that it is clear. All right. So if omega t is a mixed state, then you can write it always. If it's a mixed state, you can write it like this. Okay? That just says that it is an incoherent superposition. Now the point is that for an event to happen, I would like these pi xi's to be somewhat special projections. Namely, I would like, you see, if you form any operator out of the pi xi's, let's look at the x, which is some kind of function f of xi pi xi. Then it follows from this equation that the adjoint action of x on omega t vanishes. Okay. Now, for an event to happen, I would like this operator x to belong to the same algebra as the operators on which I evaluate my state. So I would like x to belong to e greater or equal to t. Right? That sounds reasonable. Okay. Now, then you conclude that apparently from this condition and from this condition, you conclude that x belongs to the centralizer of the state, omega t, on this algebra. Is that also clear? No, I mean, that's just the definition of the centralizer. If that's not clear, you just believe that this is the right definition. Yes?
Can I summarize what you have said by saying the following?
Please. But you have to speak loud, otherwise the lady doesn't hear it.
You see, normally you hear, when you hear the quantum mechanical formalism, you hear something about pure states, reduction of the wave packet, and so on. What Jörg is proposing is a formalism which is more involved, in which he has these algebras which are filtered, okay? And in which what he proposed is that the evolution of the state actually can only be of the type which is here. Namely, when we were talking about reduction of the wave packet, in fact, Jung is asserting that what you are doing, you are taking a reduction with respect to the center of the centralizer, and this occurs in a certain specific manner. And so he is asserting that this is the way things occur in practice, okay, and that somehow this is a correct conceptual understanding of the quantum mechanical formalism.
Yes, this I understand, but my question was more basic. What is an event, and can one imagine a continuous sequence of events in the evolution of a system, or how should I imagine?
So, you see, the idea is the following. But I mean, you know, at some point we will probably have to stop because you want to go and have dinner. But let's maybe make a comment on this.
I'm sorry, I'm a physicist, so I would like to have a more intuitive understanding of the notion of it.
Well, we all would like, you know, if things were easy, then we would all understand it, but it's unfortunately not such an easy thing, although the mathematics is basically still absent. Then once we add the mathematics, it will become even more difficult.
If you want, we can make it a more private discussion. I don't know.
Well, maybe this can be answered very quickly. You see, suppose some event happened at time t. Then let's discretize time. It's a little more, since you are a physicist, this is more intuitive. Then I march from time t to t plus delta. And I ask, is there an event happening? Well, with, you know, with extremely overwhelming probability, the answer is yes. So there will be several projections, pi psi 1 of t plus delta, pi psi n of t plus delta, describing the event that may happen at t plus delta. But only one of them will have an overwhelming probability of occurrence. If delta is small, then maybe omega t plus delta of pi psi 1 t plus delta will be 1 minus a very tiny quantity, and all the other projections will have an extremely small probability of occurrence. So then what happens usually is that you just pick the projection with the overwhelmingly large probability. Then you would say, well, then, you know, the whole picture becomes almost the same as the Schrödinger evolution, because whether I now choose the state omega t plus delta or the state omega t plus delta pi psi 1 t plus delta pi psi 1 t plus delta normalized, it makes essentially no difference. These two states are almost the same. Then I go to the next step. Again, there will be an event happening, but one of the possible projections will have an overwhelmingly big probability of occurrence. So you could say, well, that this picture is just a more complicated version of what you learned in school. The problem is, if you do this n times, and you always choose the projection with the biggest probability and ask, what is the probability of the history? It's exponentially small. So every once in a while, you have to pick one of the projections that is unlikely to appear, just for, if you like, entropic reasons. And then you can say, these are the times at which, as a, you know, observer with not entirely sharp eyes, you really see that an event happens. Does that?
I think it's more clear.
Now, there are toy models illustrating these concepts. You could look at Limpladian evolutions of density matrices and implement these ideas about events in conjunction with Limpladian evolutions. This leads to some interesting mathematical problems. I could give you a full story in the example of 2 by 2 matrices, which is maybe not so exciting. If you go to m by m matrices and you want to know exactly how these trees of possibilities and the histories and so on look like, just in the example of Limpladian evolution, is already very difficult. And one of the reasons why it is difficult is that we don't quite know how to parameterize density matrices in an efficient way. So in fact, I have no very explicit results to offer about that. But I think that's something that could now be attacked by people who know more mathematics than I do.
Let's thank our speaker.
Okay.